Hello and welcome back to Calculus 1, section 2. You are looking for the answer to be infinity. Infinite limit. The answer that I get is infinity. Limits calculate y value. So if I have infinite limit, that means the answer is infinite, meaning we are looking for this particular situation. Limit as x goes to a of some function f of x is equal to positive or negative infinity. So this is what we are looking for in the entire section. And by the way, lesson is over, right? We already had an example of this on the first day, which was the limit of 1 over x squared, if you remember. So one of the perfect examples here, limit x goes to 0 of 1 over x squared. And we said that was positive infinity. Why? Well, because graph, right? The graph looked this way, so you get Romeo and Juliet to approach 0, and they both agree on positive infinity as the answer as they approach, right? So remember, 1 over x gave us does not exist, because one limit went to negative infinity, the other limit went to positive infinity, so they did not agree. But in this case over here, both are going to positive infinity, so we are all good. Now it doesn't stop here. Also, one-sided limits that always have some kind of answer can be also positive or negative infinity. So added to this line up there are going to be the one-sided limits x goes to a minus, this is Juliet, right, approach from the left, of f of x is equal to positive negative infinity, and finally Romeo was blue, so we're going to do the limit x goes to a plus of f of x to give us also positive and negative infinity. And I'm going to box these as well, because these are the one-sided limit versions. So that's the over limit, and this is the one-sided infinite limits. I have nothing else to say. That's it. Now the bigger part of this lecture is the application of these. There is something in mathematics that is extremely important, and it's defined by these limits. And its name is vertical asymptote. I was hoping someone would know it, so I there was dramatic pause right there. Vertical asymptote. In pre-calculus, you got a little flavor of vertical asymptote. And then professors were very careful which problems are given, because you did not have a full definition of the vertical asymptote. So clearly, certain examples would not go well. You learned something dangerous, and that is you set your denominator equal to 0, and that's the vertical asymptotes. Not quite. So we're going to fix that now. On your exam 1, I might ask you to define vertical asymptote. You are supposed to write the definition for the vertical asymptote. So here we go. Vertical asymptote VA. I'm not going to spell it out every time. Vertical asymptote is a vertical line at x equals a, for which limit x goes to a of f of x is equal to positive or negative infinity, or limit x goes to a minus of f of x is equal to positive or negative infinity, or limit x goes to a plus f of x equals positive or negative infinity. This is your vertical asymptote definition. So vertical asymptote for a function f of x, maybe I should have put that in as well, vertical asymptote of f of x, happens at the point x equals a where any of the three limits are true. Not all three, but any of them. So if at least one of these is true, you have a vertical asymptote. Let's take a look at examples. My favorite example is function ln x. It has vertical asymptote at 0. And you are only allowed to do Romeo approach, which is from the right. The function for ln doesn't exist on the left-hand side. So if you take a look at ln function, which is like that, going through 1, your ln x, log base a of x, it doesn't matter. They all go through 1 and they all look the same. Over here, you have a vertical asymptote at 0. If you take the limit as x approaches 0 plus, because you have to approach it from the right? So we have a plus on a 0 of ln x, you will get negative infinity. And that over there immediately says vertical asymptote at x equals 0. Previous example of f of x equals 1 over x squared, right, was the graph that looked like that. We can take the over limit here because the over limit worked just fine. X goes to 0 of 1 over x squared. It was positive infinity because both sides agreed on positive infinity. Another example would be f of x equals 1 over x. Well, now overall limit does not exist, but we don't care about that, right? Because any of the three limits which would give you positive or negative infinity would reveal the vertical asymptote. So let's pick Juliet here, right? The approach from the left would be enough for us to know that there is a vertical asymptote at 0. Because approach from the left would be limit x approaches 0 minus, that's from the left, of 1 over x is equal to negative infinity. Again, there is a negative infinity, so vertical asymptote. So this part over here says VA at x equals 0 because you got infinity. So you have all three examples. Approach from the right. Both approaches are agreed to same infinity, so that's the answer. And here is on the bottom, approach from the left is used. You can also use the right. So that's that part. And now we get to the part where we fix the pre-calculus issues, right? You see, we are very careful not to give you this particular problem in pre-calc. X minus 3 divided by x squared minus 9. We are very careful not to give you this problem. Because you don't have the limit definition. And you are going to get wrong answer. What have you learned? Set denominator equal to 0 and you're done. No, it doesn't work. Look, denominator equal to 0 is x squared equals to 9, x equals plus minus 3. And then you claim vertical asymptote x at 3 and x at -3. Okay, I'll go with that for about 1 minute, and then we're going to kill it. Because now what I'm going to do is I'm going to go into calculus and take the tool, which is called the limit, to check these answers. So if these are vertical asymptotes, then the limit better give us infinities, right? That's the way. So let's go. What is the limit as x goes to 3 for x minus 3 over x squared minus 9? Well, we just learned an hour ago the way to solve this limit. It's 0 in the denominator. I can't plug in. So what do I must do? Factor and cancel. Very good. So limit x goes to 3. I have x minus 3 divided by x minus 3, x plus 3. These guys cancel, and I get 1 over 6. Is that infinity? No. Do I have a vertical asymptote at x equals 3? No. That's just
a hole in the graph.
Yes, right? It's just a hole in the graph. I'm actually going to put up a graph on the screen, so we are going to verify this graphically as well. Okay, well now we have eliminated a vertical asymptote that pre-calculus would claim is an asymptote. It's clearly not an asymptote because the definition for vertical asymptote says your limit must give you infinity. We just did the limit and it gave us 1 over 6. So x equals 3 is not vertical asymptote. Let's check the other one. Limit x goes to -3. Maybe this one does better. So I still have to do the same method, obviously, because it's the same problem. Approach is different point, but we still factor and cancel. And now you see that you can't plug in. You have 1 over x plus 3, and when you plug in -3, you get 1 over 0. Now that's a problem, right? But the good thing is that this is the cheap one to graph. So we can use a different method. Algebra failed us, right? Because we couldn't do anything with this. So now we are going to graph it because we can, right? We know 1 over x. 1 over x plus 3 does what?
Shift to the left.
Shift to the left. So we are going to put 1 over x graph there, and then come on. What do you see on a graph? What is the immediate thing you see on a graph? Without any further calculations. You see the asymptote, right? It's right there. So, if you do the Juliet approach from the left, you will get negative infinity. So, yes, there is an asymptote at -3. So, VA at x equals -3. Please do not trigger my allergies by writing this. This has no meanings in mathematics. So if you put this on a test, it's automatically -2 because you did not provide the answer. Right? Don't write this garbage. Mathematical lines are either x equals a number, y equals a number, or y equal mx plus b. That's it. You cannot say va equals to 6. Like, what is va equals to 6? This has no meaning. So don't write that. Your vertical asymptotes are x equals number. So let's say x equals 6. Vertical asymptote, let's say y equals to 3. Slant asymptote is y equal mx plus b formula of some kind. Slant asymptotes are those that are right on an angle. Good. Let's review the problem. Here's your function, and you set denominator equal to 3, And when you compute those x values, you don't get asymptotes per se. You get candidates at which or at the locations, right, where asymptotes could be. That's what you get. And then you have to do the limit and then eliminate those that do not give you infinity. Now, the second one over here, if we are to redo the limit, x goes to -3 from the left of 1 over x plus 3, we would get negative infinity, and then we're happy because the limit gave us infinity, and that's why we know that there is a vertical asymptote. Now, there is a there is a website called Desmos, which you probably used in life at some point, maybe, I don't know. And Desmos is amazing website to do graphs. However, it's not that great for this particular concept, because for whatever reason, they don't put that hole, what you said, open circle. They don't put that hole, so you can't really see it. You actually are better off looking at the TI-8384, because there will be a missing pixel at that point, so you actually can't see. Now for Desmos, I'm just going to graph this function, and it will show only one vertical asymptote at -3, and on a +3 side, it will look like function just plows straight through. It doesn't plow straight through. There is an open circle above 3, and that circle is at value 6, because that's the y value we calculated. So start graphing over here. My function is open parenthesis x minus 3, close parenthesis, divided by open parenthesis x, I don't need these parentheses, but whatever, minus 9. And oh, 1 over 6, not 6. Okay, good. So this is the graph, and you can clearly see a vertical asymptote. Can I get the 3, please? Oh, come on. To zoom so much. All right. So at -3, you see that the function goes to follow the asymptote. At 3, it doesn't. Now you can see that this is 1 over 6, so there should be 6 of these parts. 1, 2, 3, 4, 5, 6, right? At 1 over 6, and it has to be an open circle. Now, they don't have that feature, unfortunately, so if you are to use your TI-83 or 84, I did ask you to do the emulator if you have the phone, or if you already have the calculators, you are welcome to bring them to class. I can probably... Why do people mutilate this camera? There we go. Let me see if I can bring this thing. Oh, document camera. There we go. Okay, this. Just need to, because actually, why am I messing with this when I actually, something that I haven't used in years. Let's just see the battery. Oh, battery is working. Okay, good. So I'm going to go to the Y screen and then type open parenthesis x minus 3, close parenthesis, divided by open parenthesis x squared minus 9, and graph. Now, you can't tell much here because, right, it's a whole mess over here, so you can't tell. Then what you can do is you can push window button and then make it zoom in. So window, And now go down to x minimum. Now I want to display positive 3. So I'm just going to go from 2 to 4 on x. And the y, because the value is at negative 1 over 6, I can just go 0 to a half, let's say. So for y value, 0 to 0.5, which is a half. And now if I grab... Well, it tells me to quit, so class is over. This is supposed to be 4. Graph. There it is. So now you see the missing pixel, right? You see the missing pixel at 3. You know that this tick mark is 2 because in a window you set this to be 2. You set in the window that this is 4. So obviously between 2 and 4 is 3. And now you see over there that there is a missing pixel because calculator could not compute the value at that point. Do we see any asymptotes? No, we don't, right? And we clearly, zoom 6, we clearly see that there is a vertical asymptote at negative 3 and that there is no vertical asymptote at 3. So the good old story, set denominator equal to 0 and you must have vertical asymptote, clearly doesn't hold. It's not the entire story. So what we just learned is that your job is to set denominator to 0, to get those candidates for asymptotes, and then check each one. So now, here is a wording for possible exam question. Prove that vertical asymptote for function blah 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 is at 2. So your answer cannot be vertical asymptote at 2. It's given to you in the text, right? So I am asking you to prove that the asymptote is 2. What do you have to do? You have to crank the limit, x goes to 2, put the function, and just work out the limit. If you get infinity, there is an asymptote. If you don't get infinity, no asymptote, and that's it. So again, you have to check the definition and the theorem, right? Those calculations are not arbitrarily just say, yeah, it looks good. Move on. Right? And that's it. That's 2.4, limit, infinite limits. Infinite limits give us definition for vertical asymptote, and vertical asymptote plays a major role in mathematics, something that you have to avoid in about 100% of the design that you make as an engineer. Vertical asymptotes are very dangerous because they shoot to infinity. If you have energy represented as area under the curve and you have a vertical asymptote, that energy is trying to go to infinity. All right? So figuring out where these asymptotes are is extremely important, especially when you're dealing with alternative energy, when you want to create a battery or something like that, because you do not want to have unbounded energy. Unbounded means goes to infinity, right? If you cap your energy at certain amount of calories or joules or whatever you measure your energy in, then you have the capacity of the battery, the capacity of the water tank or a glass or something. They're not infinite. They're never infinite. One of the favorite examples that I have and talk about is this sense where you actually do get explosions when you have 0 in denominator. That experiment is, somewhat dangerous, but not really. Shorting the outlet. If you take a piece of insulated wire and you stick it in the outlet, you get the mini explosion. And then the fuse pops, right? And you have to go reset it. Why? Well, it popped because your limit went to infinity. The equation in electrical engineering, well, the basic one, but there are nicer ones, is that the current is equal to the voltage divided by the resistance. It's called Ohm's law, and if you took any physics ever and you had any electrical in it, this is the most basic formula you get. Now, your voltage in the outlet is 110. It's 118, but 110 volts, divided by the resistance, which is what you are plugging into the outlet. So if you have your cell phone charger rated at 2 amps, you can plug in 2 for I, and you can calculate the amount of ohms that your coil for the transformer will have to step the voltage down from, let's say, for cell phone charging down to 5.5 volts, so from 110 to 5.5. Now, when you short the circuit with a little piece of wire, the resistance goes to 0. And that is you dividing by 0. When you divide by 0, we learned in the limit that the limit, because what kind of function is this if resistance is a variable? What kind of function is this? It's 1 over x, right? That's the function. So if I have 1 over x and we look at the graph, as you go to 0, this would be your current, this would be your resistance. As you go to 0, for resistance, which is you taking a piece of wire and sticking it in both poles at the same time, the current would try to go to infinity. In a short period of time, current in physics is proportional to temperature. If the current is trying to go to infinity, temperature is trying to go to infinity. That's physics, right? So these concepts are heavily used. Now you need to find where this stuff fits. I just gave you a little taste of, later on what's happening with analysis in physics courses and so on, and why you want to have something or why you don't want to have something. And we will be talking about this particular case one more time when we work, that's Calculus 2, when we work on what we call improper integrals. Those will have vertical asymptotes in them, and they are very dangerous creatures because integral would compute area under the curve, which is energy, and if you miss a vertical asymptote in your domain, the energy becomes unbounded. Whatever you designed with that one has to explode. It has to. There's no question about it, because that's what unlimited energy is, explosion. So not a joke, right? Welcome to engineering. We're going to take a short break. When we come back, limits at infinity. Not as dramatic.